So as it is stated in the previous sentence, the variability in the sample data is measured by the sample variance. So the standard deviation, the symbol or the formula for the standard deviation is S equals square root of xi minus x average. In parentheses, we square each of them and then add them and then divide by n minus 1. So they give an example for this equation. And here comes the box plot, which is the variability symbolizing diagram, we can say, box plot diagram. Box and whisker plot, in other words, we can say. So we have 12 data. For this 12 data, we would like the data, how the distribution or the variability of the data is. So we draw the box plot diagram. Now for box plot diagram, the data is divided into 4 values. That is 25% of the data is here, and the 25% is here, and the other 25, the other 25. We calculate these values and then draw the diagram. For example, let's say that we have 3 plants. For the 3 plants production, we took the data and we drew the box plot diagrams. Now here, which one has the least variability? The third one, because it has a very short range for the values. Which one has the most variability? The second one, because it has a very large variability. Now for the quality, we wouldn't like that kind of variability. We would like as small variability as possible in order for our products to be qualified. And then we deal with the probability distributions, how the data is distributed. We would like to match the data with the distribution so that we can use the distribution to forecast the coming data, the coming production maybe. Definition for distributions is we split distributions into 2. One is continuous distribution, like normal distribution, Poisson distribution, and we have discrete distributions, like we can say fail or pass, or tail or head kind of coin drawing situations. We have the values discrete each other. So when we look at the diagram of different continuous distribution and the discrete distribution, the first one is for the discrete distribution, and we call it a probability mass function. How loaded each value is, it means. And for this one, this is the continuous distribution probability density function. So in order for, actually, why do we draw this? These will give us some idea about the population from the sample so that we can guess for the future. So there's an example. Again, another example. So central tendency is important. The mean, we can measure central tendency with 3 values. What is it? One is mean, the other is mode, and the other is median. So central tendency is important for us about how our production focuses or centralized is. So here are some different distributions. For example, in figure 3.2, 11, we have A, B, C. In the first one, the average is mu. Mu symbolizes the average of population. So sample is same as the population. We see it in the A. But in B, we see that the median is not same as the mean, the average value. So there's some kind of skewed distribution. In C, we have as if two different distributions, and each of them have different modes. We will work with these kind of situations. In figure 3.12, it gives an example for the C model. At top, the C model example, it gives that mu is equal to 10 for the first distribution and mu is equal to 20 for the second distribution. And let's compare the standard deviations when standard deviations are different. In this example, there are two distributions. Both of the distributions have 10 as the average value, but their standard deviation is different from each other. One is 2, one is 4. So what does 2 means? What does 4 means? 2 means that the distribution of the data is so close to the mean. So the target is the mean of the production, let's say, and these are the products that diverge from the mean, which is 10. So for sigma equals 4, we have a larger distribution, which is not good for quality of the product. So these are the sigma square. When you look at here, since this is the population standard deviation, or if it is squares standard deviation, it is called variance, as we see it here. So the variance calculation is, we subtract the average of the population, which is symbolized as mu, from each of the data, and then square them, square the difference, and add all the difference, then divide by big N. Big N symbolizes the population number, population size. And when we would like to calculate the standard deviation of the population, see, it is divided by big N. Since this is the population, we divide by N. But for the sample, we were to divide by small n minus 1. Now, what are the important discrete distributions? The first one is hypergeometric distribution. We can give example to this as, let's say that there are 10,000 production, and out of 10,000, let's say that we have 50 defaults, and here we write defaults, n minus defaults. We draw x from the default and n minus x from the non-default ones, and big N over the sample number. So this distribution really gives the exact, the real life situation. Actually, in our calculations, we always have to use hypergeometric distribution, but because it is a little bit complex, we would prefer to move on to the other distributions with the limitations. So there is an example. 0 is not default, but 1 is default. Cumulative distribution function for the hypergeometric distribution. So the second one is binomial distribution. After the hypergeometric distribution, we move on to binomial distribution, which is we take n samples out of n x defaults. So P is the probability of having a default, and 1 minus P is not having a default. So the average for the population is n times P, and the standard deviation or the variation is n times P times 1 minus P. The binomial distribution, when n is 15, it gives us different P values like P 0.1, 0.5, and 0.9. So these are 0.1 P values, and the black ones are 0.5. Again, the light blue ones are 0.9. Here we have P 0.25, and it changes the n values here, 10, 20, 40, and you see how it changes. So when n is large, as we can see, this distribution goes to normal distribution. Since this is binomial distribution, so this is discrete distribution, but it looks like the normal distribution. And here comes the Poisson distribution. You see the formula here. P, the probability of x number of defaults, is E over minus lambda, lambda over x, and all over x factorial. So mean and the variance of the Poisson distributions are the same for Poisson distribution, sorry. So for different lambda values, we have different distributions. Poisson is also a not continuous distribution, but as lambda gets higher, it looks like normal distribution. That is why we move from hypergeometric to binomial, from binomial to Poisson, and from Poisson to normal distribution. So there is also a negative binomial distribution. Here you see the formula changes, x minus 1 and r minus 1, and the average and the variance changes. We may sometimes use these formulas in order to understand the distribution of the data. So there are connections between the distributions. For the negative binomial distribution, sometimes it is called Pascal distribution, and when r equals 1, the negative binomial distribution is known as the geometric distribution. And for geometric distribution, as you see, we have the mean value 1 over p and variance 1 minus p over p squared. Important continuous distributions, and the most important one we use a lot is the normal distribution, and here is the very huge formula for that. It comes from minus infinity, goes to infinity. So it's a bell-shaped, as we all know, curve for the normal distribution like this. So investigating normal distribution, these values are important. Why? Because this is the range between minus 1 sigma to plus 1 sigma. So we add 1 sigma to the average, to the right and to the left. And this is 95.46% is 2 sigma intervals, and 99.73% is for the 3 sigma intervals. So in quality control, for example, we will look at 6 sigma. 6 sigma means we have 6 sigma here, 3 sigma plus 6 sigma here, 6 sigma here. So a total of 12 sigma there will be. Companies are producing that qualified products. So that's the normal distribution formula. There's an example here. We will look at the examples later. Here comes the central limit theorem. This theorem is very important, which makes us use normal distribution for expecting or for forecasting the future product. What does it say in short? When we look at the formula, maybe it's hard to just draw a conclusion, but what it says is this: whatever the distribution of the population is, the population distribution can be Poisson. The distribution of the population may be exponential. Anything. When we take samples of 5 or more, let's say, and take the average and look at the average distribution, we always end up with normal distribution. This is very important. So we don't care the population distribution at all if we take random samples of 5, which is applied in quality control. If we take random samples of 5 and take the average and look at the distribution of these averages, they look like normal distribution, which makes us control the production with the control diagrams. And there is also log normal distribution, which can be used when the data cannot be understood. The distribution of the data won't fit any distributions. We can just check whether it fits to log number distribution or not. So the shape of the log normal distribution is like this. There's an example for that. And the exponential distribution, as you know, lambda e over minus lambda x. So the mean and the variances are like this: 1 over lambda, 1 over lambda square for the variance. Again, the different graphs for the different lambda values. And the gamma distribution, the averages are over lambda and the variances are over lambda square. If we look at the previous formula for exponential distribution, only r comes in place of 1. So different r values gives us different shapes of the diagrams. Weibull distribution looks like complex. Again, there are examples. And here comes the probability plots. Normal probability plot is very important because we mostly use normal distributions. We would like to understand how the points behave. We would like to look at whether they fit normal distribution or not. So we draw some kind of graph named normal probability plot, and when we plot the data, if the points lay on the line, it means that the data is distributed normally, like here. There are other probability plots. For example, the first one is normal. Since there are some points above the line and some points below the line, they tried to use log normal distribution, and this fits better than this one. These values fit on the line better than this one, so it is better to use maybe this distribution. And they used Weibull distribution and exponential. Exponential doesn't fit that much, and Weibull also. This is the most fitting distribution. Okay, that's the end of third chapter.